of a is equal to 0, then we cannot say whether it is increasing or decreasing, but we can only say that it is a, hence it is also called as a critical point. It is a critical point of fx. X equal to a is a critical point of fx. For example, if fx is 3x cube minus 6x square plus 2x minus 1, so its derivative is 9x square minus 12x plus 2. Okay, verify this. Then let's take any 2 points, any points. So let's say we take the point x equal to 0. Then f dash of 0 is 2. Therefore it is, therefore f is increasing at x equal to 0. Okay, at x equal to 1, 9 minus 12 is minus 3. Minus 3 plus 2 is minus 1. So f dash of 1 is minus 1. So fx is decreasing at x equal to 1. Okay, verify but see whether you get the same values or not. Okay, so now what? Now we go on to the second derivative. Okay, so the second derivative of function, okay, that is d2 fx by dx or f double dash of x. Second derivative of the function is the derivative of the first derivative of that function. Okay, so if you now consider, okay, so fx was a function and the first derivative of fx is 9x square minus 12x plus 2. This is like another function in itself. When you find its derivative, you get the second derivative. So while the first derivative tells us whether the function is increasing or decreasing, the second derivative will tell us whether the first derivative is increasing or decreasing. Do you get this point? Okay, you are applying the derivative, you are finding the first derivative of the first derivative. Okay, so now f dash x is like a fresh new function and you are applying the first derivative to it, and the first derivative will tell us whether the function is increasing or decreasing at that point. Okay, so the second derivative tells us if the first derivative is increasing or decreasing. If the second derivative is positive, then the first derivative is increasing. Okay, graphically it will look like a graph being concave up at that point. That is something like this. Okay, so this is like a parabola facing upwards, concave up. Okay, you can consider this entire parabola facing upwards if it is positive. If it is negative, it is facing down, parabola facing downwards. Okay, you can consider this as uh, all of you know about a parabola, right? The graph looks something like this. Okay, okay, so what it means is, So at this point you got your first derivative 0. After this the slope is going to increase. The first derivative is going to increase. Then the second derivative will be positive. And here it is 0. And after this the so the first derivative is increasing after this point. First derivative is increasing. Okay. Decreasing, sorry, in this case it is decreasing. Okay. So if f double dash at x equal to a is greater than 0, then fx is uh, okay, let's continue this discussion a little bit. So you got this point that it is concave up, concave down. The next point is, okay, now at the critical point of the function, we we cannot say anything about, okay, when f dash of a is 0, that is x equal to a is a critical point of fx, we cannot say from the first derivative whether the function is increasing or not. Okay. Now there is something called as the concept of local maxima, local minima, and global maxima and global minima. I'll try to share an image here. Okay, I hope you can see this image. So this is a local minimum, global minimum. Okay, these are the local minimums, minima actually. In so so in general they are called as extremas. Okay, so maxima and minima. Okay, so in this case they have shown multiple global maxima, but you can also have a single peak like this. This will be a local maximum and that will be a global maximum. Okay, so in this case there are multiple values of x at which fx is at the maximum, at the global maximum. So there are all these points of x, all this range of x will be your global maximum. But first let's try to find whether, okay, so first of all the observation is, this is actually this was actually a result by Fermat. So whenever we have an extrema at x equal to a, f dash of a will be 0. This is a result. This is a you can call it a theorem. Okay. Whenever we have an extrema, so at all these points, okay, at this point, at this point, this point, okay, whether it is maxima or minima or a multiple kind of a maxima, plateau, you can say. So the terminology is whenever, so okay, so normally maximas are called as peaks and minimas are called as troughs. And such cases where there are multiple global maximas or multiple minimas, those are called as plateaus. Okay. So from the second derivative, you can find out whether f dash of a equal to 0 means it is a local. You cannot say anything about global, okay, but you can at least say that whether it is a local maximum or minimum without plotting the graph, obviously. Okay, one way is you can plot the graph and you can see what is happening, but if you don't plot the graph and you just want to perform the analysis numerically in this method, then you can say that if f double dash of a is uh, so the first condition is okay. So okay, for all these, when f dash of a is equal to 0 and first case f double dash of a is greater than 0, okay, it means fx has local minima at local minimum actually. Minimum is singular, minima is plural. Local minimum at x equal to a. Secondly, when f dash of a is equal to 0 and f double dash of a is less than 0, it means fx has local maximum at x equal to a. And now still there is a tricky case where if f double dash of a is also equal to 0, which normally happens in case of a plateau, okay, because the first derivative also stays constant in this region, so it happens in such a case. So here we we can say that no new information about fx, no new information about fx. But in this case, okay, so if we consider the second derivative just at somewhere at this point, let's say, where the f dash x first becomes 0, okay, then because we consider it going forward, let's say, here the second derivative also becomes 0 slightly before this point. If we take where the curve just ends and uh, the peak just starts, it may happen that we can detect the characteristic like a maxima. Similarly, at this point just before it begins to fall in a way, we can detect it. In between all these points, we'll have double derivative equal to 0, no new information. So still using these points, we can detect whether it is a maxima or not. Okay. In other cases, it is straightforward. Even in this case, it's a local maxima, local maximum, local maximum, local minimum, local minimum, local minimum. And then you can actually, to find a global maximum minimum, if it is possible in this way, what you can do is you can substitute you can find the actual function values at those points and then you can see. So for example, the function that we had considered earlier, okay, let's take another function. Okay. Let's say f of x is x cube minus x cube minus 9x square plus 15x minus 7, okay, minus 7. So if you are asked to find the local and then global, or let's say just the local maxima minima, okay, you can take a range and you can just find the, it depends on the function. So in this case, let's see, let's proceed with this. Let's first find the critical points. Okay, if it's a repeating periodic function, then it doesn't make sense. But in this case, we can find uh, the points. Okay. So first derivative will be 3x square minus 18x plus 15. Now you will have to solve this quadratic equation. To solve this, you will have to equate it with, okay, we want the critical points, okay, at which f dash of x is 0. So solving for common factor of 3 throughout, 6x plus 5 equal to 0, x square minus 5x minus x plus 5. So it will be x minus 1 into x minus 5 equal to 0. Therefore, x equal to 1 or x equal to 5. These are the two critical points for this function. Okay. So f dash of 1 is 0 and f dash of 5 is 0. Now let's find a second derivative. F double dash of x is 6x minus 18. Okay. Now at x equal to 1, it is 6 minus 18, which is minus 12. Okay. And at 5, it is, which is plus 12. Okay. So we know that there is either a peak or a trough at x equal to 1 and x equal to 5. This tells us that there is a local maximum at x equal to 1, and this tells us that there is a local minimum at x equal to 5. Okay. Now I'll stop for a minute. Any questions, any doubts? I'll also see the chat. X equal to 5 and 1. Yes, Hemant. Any questions, any doubts up to this point? Okay, so I'll proceed. Okay, someone has posted something. We consider this when f dash of a is 0. Yes. Can f dash of x equal to 0 is called a constant? No, I did not get that point. When f dash of x is equal to 0, then that particular x is called as the critical point. And f double dash of, yes, no, no. In this case, it's opposite. So when why at negative value? Because, okay, I'll try to explain that. This is opposite actually. So opposite in the sense, when you get a negative value, it's a maximum, and when you get a positive value, it is a minimum. Okay, so because, so first let's consider why it is minimum. Because, okay, if you consider the value of the slope, okay, so when the slope is like this, it is a negative, it is called as a negative slope, and when the slope is like this, it is called as a positive slope. Okay, this is negative slope and this is positive slope, because we are reading the graph from left to right in that way. Okay, x moves forward from left to right, so this is our positive slope, and y increases, or the the fx axis or the y axis increases from down to up. So this is positive slope, this is negative slope. So at this point, okay, the slope was negative, 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 negative. Then it became 0 over here, and now it is a minima, and now the slope will begin becoming positive. Okay, slope was earlier, magnitude of the slope may be the same at these points. Okay, let's say at this point and at this point, magnitude of the slope is the same, but the sign is different. So here the slope is negative, then it becomes 0 at the local minima and minimum, and then after the local minimum the slope starts becoming positive. Okay, slope starts becoming positive. So if you see, yes, you got the point, right? Slope becomes negative to positive, therefore it increases, and at a maximum the slope was earlier positive, 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 then it becomes 0 here, and now it starts becoming negative. So positive to negative, therefore the slope decreases in a way. Okay, so that's why. Mahesh also got the point. Yes. So the next thing is inflection points. Okay, inflection points, and then we'll move on to the case with more than one variables, and then finally to gradient descent. So okay, now, okay, not going into quite. Okay, so if f dash of a is equal to 0, then the function looks something like this. Okay, either it is a plateau as we discussed before, or it is something like this. You can see this in the second graph actually, if you have this. I- and the main point is, so it's not like this or like this. It's something like it was becoming a peak, but then it just flipped and it became that. Okay, so inflection point is when the, or it can be other way around. Okay, so for example, if it was a something like this and then it became suddenly like this, it changed its orientation. So the function was becoming concave up actually. If we track from this point, it would have become concave up, but instead of going concave up, it suddenly flipped and instead became concave down, this function. Or it was becoming concave down and instead it became concave up. So such a point is called as an inflection point. This is not relevant. Such a point or a plateau as we saw before, but this is the important case where it is called as an inflection inflection point. So for example, fx equal to x raised to 4. Okay, then f dash of x is 4x cube. Okay, and this is 0 at x equal to 0. Okay, and we have f double dash of x, which is 12x square. Okay, so at x equal to 0, f double dash of 0 is 0. Now I'll try to show you how this function looks, x raised to 4. We'll share this tab. This is how x raised to 4 looks. Okay, x raised to 4. So if you see carefully at this point, okay, this is also a case of an inflection point, because all of these are, so x, this is not a local minima as such, but in fact all these values in this range are, okay. So, and that is because if you see how x cube looks, okay, this is what inflection point I was talking about, okay. Till here the function was like concave down, so here would have predicted that it is a peak, but then it suddenly changed and it became a concave, uh, convex, uh, up basically, okay. So I hope you get this point. Okay, so let's now move to uh, the case where there are more than one variables, okay. Can you see the whiteboard? Okay, so okay, so now in case of more than one variables, let's consider case with two variables. So let z is equal to f of xy, then x, uh, instead of saying x equal to a, let's just say x equal to xc and y is equal to yc, okay, or in short xc comma yc is a critical point if the following conditions are met. First is uh, fx, that is the partial derivative of f with respect to x at xc comma yc, is equal to partial derivative of y at xc comma yc, which is 0. Either this or, okay, both cannot hold. Either this condition holds, or instead of saying 1 2, it's like either this holds or fx, that is the first, that is the, it is the first partial derivative of f with respect to x at the point xc comma yc does not exist, or fy xc yc does not exist. Okay. First condition is both the partial derivatives are equal to 0, or one of the partial derivatives does not exist. Then xc comma yc is called as a critical point. So for example, if f of xy is x square plus 2xy uh, minus 4y square plus 4x minus 6y plus 4. So in this case, partial derivative with respect to x is 2x plus 2y, which is constant. This is plus 4, and partial derivative with respect to y is 2y, sorry, 2x minus 8y minus 6. Okay, now we cannot say that one of them does not exist, so both of them do exist. So the only condition is to find the critical point is equate both of them to 0. Okay, so 2x plus 2y plus 4 equal to 0, and 2x minus 8y minus 6 equal to 0. Now this is like solving a simultaneous set of two simultaneous simultaneous linear equations, as we have seen in the previous semester also. Okay, can you solve it and tell me the values? Again, you don't have three equations here. You have only two equations, so you will have to assume some value. So I'll solve this. Let's say you can just verify. So if I subtract this, okay, this is, let's say, 1, this is 2. So if I perform 1 minus 2, it will be 10y equal to minus 10 and y equal to minus 1. Okay, and if you substitute it back in one of the equations, let's say 2x plus 2 into minus 1 minus 2. So 2x plus 2 is 0. So x is also equal to minus 1. So minus 1 comma minus 1 is the critical point of minus 1 comma minus 1 is a critical point in this case. Okay, now, okay, did you get the same answer, all of you? I hope. Yes, yes. Okay, so, okay, now finding global and so finding the extrema now. Okay, so again going for, okay, now in this case, in case of two variables, we have a method. Without going to the second derivative, we have a method to find the maxima and minima. Okay, so I'll just, okay, there is a method called as completing the squares, which is not possible in this case because we have an xy factor over here. So here we can complete a square in a way. No, okay. So it won't be possible in this case. Okay, let me give another example. In which case we can find out the um, whether it is a. We'll also go to the second derivative test, but before that, there is an interesting thing that happens here. So let's say our function is x square plus 6xy plus y square. Okay, so we try to complete the square. Okay, so a plus b square is a square plus 2ab plus b square. So x square plus, now you cannot do anything with the 6xy. Okay, so uh, keep 6xy as it is. If it is 2ab, so your a is as it is x, b must be 3y. B must be 3y, and 3y square is, square of 3y is 9y square. Okay, plus y square, and then minus 9y square because you added plus 9y square, therefore you subtract it. Okay, so now this becomes x plus 3y square minus 8y square. Okay, okay. The first derivative of this is, let's say this is f of xy. So first derivative is 2x plus 6y equal to 0, and first derivative with respect to y is 6y 6x plus 6x plus 2y equal to 0. Well, as you can see, 0 comma 0 is the critical point of this, was y equal to minus 3x. You substitute minus 3x over here, then it becomes minus 16x equal to 0, but ultimately 0 comma 0 is the critical point. If you substitute y equal to 1 over here, so there are multiple solutions to this. There are multiple critical points in this case. Okay, so let's say if we consider this critical point as 0 comma 0. Okay, In this case, it will be a saddle point, which will, okay, I'll tell you later. I'll come back to this example. Let me first take another example where we get some other first derivatives. So where we have some lower order terms, then we'll not get this problem. So let's say f of xy is x square minus 6x plus y square plus 10y plus 20. Okay, now here it's quite simple, no xy term. So one square will be of the form x plus some constant square, and another square will be of the form y plus some constant square. Okay, so x square minus 6x you already have. So a minus b square is a square minus 2ab plus b square. So 2ab, a is already x, so b has to be 3. Okay, so 3 square is 9. Okay, and in case of y square plus 10y, so the if you consider a plus b square, a is y and b is 5, so y square plus 10y plus 25, these squares are completed. Okay, then you have this constant term 20 minus 9 minus 25. It is nothing but x minus 3 square plus y plus 5 square minus 20 minus 9 minus 25 is minus 14. Okay, so this actually matches with an equation z is equal to x square plus y square, which is a three-dimensional shape called as paraboloid. Okay, it's like a parabola but in 3 dimensions, so it opens upwards. Okay, so this is a paraboloid, and its critical point is its minimum point because it opens upwards. 3 comma minus 5, where so x minus 3, this is x is equal to x minus 3. So if I, okay, how did I get this 3? Because capital X is small x minus 3. If I set it to 0, that is capital X equal to, for this parabola, that is z is equal to x square plus y square, its minima is at the point x equal to 0, y equal to 0, because it opens upwards. So it is x equal to 0, y equal to 0. So x minus 3 equal to capital X equal to 0, which is small x minus 3 equal to 0, and capital Y equal to 0, which is y plus 5 equal to 0, will be its minima, its minimum. Okay, so now adding this term does not make any difference as such. This is of the form. So if you say minus 14, when you, so at the point x equal to capital X equal to 0 and capital Y equal to 0, this z will be at its minimum, that is minus 14. Okay, so the absolute minimum value of this function f of xy is at the point, okay, this is the absolute minima of this function, and the value at absolute minima is, value at absolute minimum means its absolute minimum value actually is equal to minus 14. This is the point where you get the absolute minimum value, and that absolute minimum value is minus 14. Okay, Do you get this point? Okay, fine. Okay, I'll try to show you a figure of paraboloid, then it will be clearer, I think. This is from Wikipedia itself. Okay, this is x square plus z is equal to x square plus y square paraboloid that opens upwards. Okay, and these are some other such shapes. So this is hyperbolic paraboloid, this one, and this is elliptic paraboloid. We are interested in this elliptic paraboloid. So this is a known shape, and its property is that uh, it has the minimum point at x equal to 0 and y equal to 0. Okay, so if you can bring your function in this form such that it is x terms square plus y terms square, okay, then you can write this x terms as a capital X, x minus 3 write it as a capital X, y plus 5 write as a capital Y, okay, and it is of the form of a paraboloid, and the minimum points are x equal to 0 and y equal to 0. But if you substitute x equal to 0, it actually means your small x is equal to 3 and capital Y is equal to 0 when your small y is equal to minus 5. So small x equal to 3 and small y is equal to minus 5 is your absolute, is the point where you will get your absolute minimum, or in other words, global minimum. Okay? Global minimum, and the global minimum value of the function is minus 14, because when you substitute capital X equal to 0 and capital Y equal to 0, then Z is equal to minus 14. So the minimum value is minus 14. Okay, did you get now how it is minus 14? Because even if you substitute in this equation, you will also get minus 14. Basically at x equal to 3, this term will vanish. At x equal to 3 and y equal to minus 5, you substitute here, these terms will vanish and there will be only minus 14 left. which will be the value if you substitute it in the function. Okay. If still you have a doubt, you can unmute and ask. Kavita and Aniket, did you get it? Actually, in fact, you don't. Okay, so this is not compulsory. Actually, we have the second derivative test. This was just a shortcut or uh, another method you can say to find whether it is a maxima minima. That's why I covered it. Okay, we'll also have second derivative test. Okay, which we'll cover in tomorrow's lecture maybe. Okay, and I'll end the today's lecture here. Any questions, any doubts? If anyone has, you can ask. I'll start the attendance now. What if we take another critical point? That is true only in case of the previous function, not in this case. In this case, okay, okay. In this case, it has something called as a saddle point. Okay, which I'll discuss in because the time is up. Otherwise, we'll have to wait for some extra time. There is something called a saddle point. I'll explain in tomorrow's lecture maybe. So here at there is no we cannot determine directly. So there is a saddle point here basically. But in this case, there is no other value at uh, as such. You cannot take any other value for the minimum point because the paraboloid has this fixed shape where it is minimum at x equal to 0 and y equal to 0. It is fixed. So x equal to 0, y equal to 0 is fixed. That is capital X and capital Y. And when you substitute, uh, like when you say in terms of small x and small y, it is 3 and minus 5. How to find absolute maximum by completing the squares method? So in that case, it will be a downwards facing. Okay, so the equation in that case will be, so after completing the squares, if the equation you get is of the form uh, minus x square minus y square and some other term. So it will be a downwards facing paraboloid and its maximum point will be at this point. Okay, so for I'll give you an example. Let's just see this example, then I'll take attendance. So for example, if it is 12 minus 3x square minus 6x minus y square plus 12y.
Sir, we cannot see the screen. Are you
Okay,
sharing it?
okay, okay. Oh, sorry, sorry. Okay, I was writing on the whiteboard. So yes, yes. Okay. So here, okay, let's say this is the function 12 minus 3x square minus 6x minus y square plus 12y. So in this case, if you complete the squares, uh, it will be minus 3. Okay, so x square plus 2x. So these terms are a common factor of 3. So I minus 3. So I took minus 3 out. So x square plus 2x. And to complete the square, we require a 1. And in this case, we have minus 1 y square minus 12y, and 12 means b is 6, so we have 6 square, that is 36 over here. Okay, and 12 is a constant we had already. Apart from that, now we have uh, minus 3, which we introduced, so we'll have to compensate with plus 3, and we introduce minus 36, which you have to compensate with plus 36. Okay, so it becomes 51 minus 3 x plus 1 square minus y minus 6 square. Okay, in this case it is f of xy, f of xy is like minus of x square plus y square, of the form minus of x square plus y square. And because you can see the square terms here, in this case x square and y square terms are negative, so it is of the form minus x square plus y square, and it has the critical point at x equal to minus 1 when capital X will be 0, and y is equal to 6 where capital Y will be 0. Okay, so it's a paraboloid opening downwards. So it's like the reflection of this one. Okay, it's like the reflection of this one just opening downwards. So in that case we can say that this is the point of maximum. Just it is the global maximum of this function. X equal to minus 1 and y equal to 6 gives the global maximum, and when x equal to minus 1 and y equal to 6, the global maximum value global maximum value is 51. Okay, okay, did you get this example? Okay, so I'll cover saddle point and then further topics in tomorrow's lecture. Let's take the attendance now.